Hi, everybody, and thank you for joining us today for CUI test results, Understanding the Corrosive Mechanism. My name is Kim Melton, and I'm going to be your moderator for today's presentation. Before we dive into introductions, I did want to go over a few logistics. First off, if you have any questions or concerns throughout the webinar, you can submit them to our panel during the presentation at any point via the Q&A box. And that's a feature. If you don't see the Q&A open on your screen, there's a list of circle buttons down at the bottom of your screen, and one of them should have a Q&A in it. You can open that to open the dialog box and then use that to submit your questions. Also, we're frequently asked whether or not we send out these presentations upon their conclusion, and while we don't actually send out the presentation itself, we do post a recording of it online for you to watch at your leisure or even share with your colleagues. This ensures that you can have the presentation within its full context. And additionally, we will follow today's webinar with a survey, and this is your opportunity to provide us with feedback on how we did today. So we're continuously striving to improve and evolve these webinars. So if you have any questions or comments or suggestions as to how we can better accomplish this, or even if you feel like maybe we've missed the mark today, we'd encourage you to fill out the survey. Now, we use this feedback to improve our webinars and provide the information that has the most value to you. The survey is part of how we deliver the JM experience to you. Now, the JM experience is based on 4 pillars of our culture here at Johns Manville, and that's people, passion, perform, and protect. And we believe it's critical to make sure that we hear and understand and respond to your needs in order to deliver the best interaction to you. So we offer webinars like this one to help educate the market and offer a tool and a resource for you and your business. And but we understand that's not really just a one-way street. Your feedback is a key component to helping us evolve to better meet your needs. So with that, we'll go ahead and dive into some introductions with our panel.
Thanks, Kim, and good afternoon to everyone. My name is Ames Kulprathipanja. I've been with Johns Manville for almost 12 years and have worked in a number of capacities in the building insulations, performance materials, OEM, and industrial business units. I'm currently the Innovation and Industrial Insulation Technology Leader within the Insulation Systems Division. I earned my bachelor's degree from Iowa State University and Ph.D. from the University of Colorado Boulder, both in chemical engineering. Marybeth?
Hi, my name is Marybeth Jones. I've been with JM for 6 years now. I'm currently working in product development for our rigid industrial insulations. Prior to joining Johns Manville, I spent 5 years in refining, and my background is also in chemical engineering.
Hello, everybody. This is Juan Carlos Madeni. I am the Metallurgy and Advanced Materials technical leader here at Johns Manville. I have been with Johns Manville for about 5 years, and in my position, I lead the R&D efforts in materials research, those materials that are used in glass processing. My specialties are in design, performance, and recovery of high-temperature superalloys, precious metals, and ceramics. Great. We would like to, let me give you an overview of the items that we'll be discussing today in this webinar. We will be talking about the understanding the corrosive mechanisms, the types of corrosions. We'll talk about the NACE TG 516 test protocol, the results from long-term CUI testing, and how the XOX corrosion inhibitor works. Understanding the corrosion mechanisms. Before we begin this part, it is necessary for me to tell you that the information provided in this next few slides is very basic to understand corrosion. I'm sure in the audience we have people with very strong backgrounds in corrosion, while others may have strong backgrounds in other items, other fields, but are interested in quickly and in simple words understanding corrosion. So this presentation will provide the very, very basics of corrosion. So what is corrosion? That's a question that we all ask ourselves. In essence, corrosion is a process by which the material deteriorates, becomes worse than the initial design state. Corrosion is easy to recognize because generally the material changes color, becomes rusted, consumed, eroded, and if significant, then the corroded part changes in shape and may not be useful. Therefore, it fails to the purpose that the part was created. For example, in the picture on the left, we have here a key that has been corroded. And as you can see, the corrosion is extreme, that if you try to use this key to open a door, for example, it probably will not work because it already lost the geometric details of the key. That is due to corrosion. In technical terms, corrosion is a thermodynamic process by which the overall energy of a system is reduced. Okay? For example, when iron ore is found, let's talk about the key in this case. When iron ore is found in nature, it's generally in the form of iron oxide. This can be hematite or magnetite, or it can be in the form of iron sulfides, like pyrite, right? Then a lot of energy is needed to process this ore by metallurgical processes to obtain iron, make it steel, and then more energy is needed in order to make a part. So the steel we touch, the key we touch in this case, is a material in a higher state of energy. As we use this key, this material, it wants to turn back into the original rock material, especially if this key is exposed to specific environments that we'll talk later. The key wants to lower its energy. It does that by corroding. But it depends on how accessible are the components to make those minerals. Like I said, hematite, magnetite, pyrite, and all of that. So we are talking about oxygen and hydrogen. In the image on the right, the system, you can really see, for corrosion to happen, you have to have a metallic part, metallic component or part, and the environment that surrounds it. In this case, we're talking about aqueous corrosion. So it is a liquid that is surrounding the material. The factors, the common factors that will influence corrosion are the physical state, gas, liquid, solid, whatever the environment is, and the chemical composition of the metal, the material, the temperature of this system, and even the velocity of this solution, this liquid that is in there. Is it moving? How fast? Is it rotating or flowing? Okay, and if there's any loading conditions, external loading conditions, is it under pressure? All of that, and the material condition. So the reasons for corrosion to occur, let's evaluate some of those. Let me explain the images on the top row first, starting from the left. Assuming this is an aqueous environment, if you have a metal joined to another metal, the potentials in the surfaces of these two metals will be different, even though the aqueous environment is the same. This potential difference will start corrosion. In the second image, as you can see, we have the same similar aqueous environment, but we have a stagnant solution due to perhaps a small defect on the metal surface. The potential difference between the locations 1 and 2 there can also start corrosion. The next image shows a pipe. Right now we know that hundreds and thousands, perhaps thousands of miles of pipes are placed into the ocean in the petroleum industry, right? If the pipe is vertically located into the ocean, the position in location 1 compared to the position in location 2, there will be a difference in concentration of oxygen. Okay? This difference will also cause a difference in potential, and that difference in potential will start corrosion also. The image on the right shows a material exposed to higher temperature conditions. One of the ends, in this case the top end, is at higher temperatures than the lower end. The difference in potential that these two locations will cause will also start corrosion. And looking at the images on the bottom row, starting from the left, the metal in this case has two small defects in there. The concentration of the sulfates are different. In fact, the sulfates in there are different. The potential difference that is generated when the sulfates are in contact with those locations of the metal also will cause corrosion to occur. The image on the right, on the bottom, if we have a metallic part which has a wet packaging material on top of it, like shown in the picture, this packaging material can be a cardboard material, a bad coating material or something, but the key is that the potential in that location, which is indicated by number 2, compared to the potential in location number 1, is different, and that difference will cause corrosion. Another reason that is not written in this slide, but also can cause corrosion, is when the material was not designed for the specific environment, meaning material selection problem. To understand corrosion, we need to understand very basic concepts. We are talking about aqueous corrosion in this case, right? Electrochemical corrosion, that's the electrochemical cell that we need to understand. If you see the image on top in this slide, there are 4 main components for corrosion to occur. You will have an anode, you will have the cathode, you will need to have the electrolyte, and you will need to have the ionic path, the electronic path, where electrons will be flowing. If any of these components are missing in the system, that will lead to avoid corrosion. But if all of these components are present, corrosion will happen. The equation that's written right there on the right is it's an example of how iron corrodes. So there has to be the metal system, which is iron, and then you would have water and oxygen, and the reaction will form ferrous hydroxide. Again, if one of these components, water or oxygen is not present there, corrosion will not happen. The second concept is solution chemistry. So it is important to know more details about the solution that's in there, the conductivity, the pH, the reactivity of this solution. All of those aspects are important. Another concept is corrosion rate and rate allowances. Corrosion rate is very important in corrosion because we would like to know at what rate corrosion is happening in the parts that we are using, correct? But it's not easy to calculate. The easiest way is when corrosion is uniform, because when corrosion is uniform, you can remove the corroded product and then determine the amount of the material that was eaten away in a specific time. So if we do that, we'll be talking about corrosion rate in terms of probably mils per year or certain volume per time, right? And if we know the corrosion rate, we can use the rate allowances during designing the system that we want to design, okay, prior the material is put into service. Another concept that we also need to make it clear is that the material can be in 3 different conditions. It can be in an active condition, as shown right there in the image on the bottom. Corrosion is happening on the surface. This material can also be in a passive condition, when there is a passive layer outside in the surface of the material, or it can be in an immune condition. We will all like to be in that third condition, correct? The immune condition, where the materials are not corroded. In order to get there, material selection is very important. Now, in order to understand very well corrosion, we need to talk about the thermodynamics of corrosion, aqueous corrosion. The electrochemical reaction has 2 half reactions. One is the oxidation, where the loss of electrons occurs, and that is at the anode. The other half reaction is the reduction. The gain of electrons occurs, and that is at the cathode. The half cell reactions are written there. The blue is the oxidation reaction, where metal is losing 2 electrons, and the half reaction in red is the reduction reaction, where we are gaining 2 electrons in that reaction. Well, then we can write a full reaction. However, no net accumulation or electric charge has to occur. The rate of oxidation must equal the rate of reduction. The image in there, it shows a small part of a material, of a metallic part. The right side in the bottom becomes the anode. So it's losing 2 electrons. These electrons are going towards the cathode there, that is on the top part of this image. We'll talk a little bit more of this reaction in the next slide. So, the types of corrosion. There are several types of corrosion. The most important ones are summarized in the next slide. Before that, let me just show you some examples of corrosion. The first one, on the top row, the image on the left shows the similar metal corrosion. You can see there the bolt and the nut are two different materials. Just because these materials are different, it can cause corrosion. The image on the middle shows a chain that was exposed to seawater, and you can see uniform corrosion on the chain. The image on the right, you can see this is a metallic material that was exposed to the environment, probably with a lot of humidity, and corrosion also happened there significantly. In the bottom row, the image on the left shows significant pitting corrosion. A lot of pits in this surface, but also you can see in the same surface there are locations where no corrosion has touched. This is a very unique type of corrosion that we'll be talking about a little bit more in the next slide. The picture on the right, on the center, just shows the rust on steel, again showing more uniform corrosion. And the picture on the right shows steel structure of a bridge that is near seawater and was exposed to that seawater environment, so it is corroded uniformly there. The forms of corrosion are summarized in this slide. The first image on the top shows no corrosion on the material surface. The material is the rectangle in the bottom. The second one shows uniform corrosion. As you can see, some of the thickness of this material has been lost, so uniform corrosion. The second one, or the third one right there, is a galvanic corrosion. Galvanic corrosion happens when you have a specific material, assuming steel, it is joined to a more novel material, and galvanic corrosion can start there, right there at the interface. The other type of corrosion is intergranular corrosion. Intergranular corrosion starts from the surface of the material, and it propagates generally to the grain boundaries of the material. As you can see, it can cause significant damage inside the material. The next form of corrosion is pitting. Pitting is kind of similar to intergranular, but it has a different mechanism because it starts at the surface, that's the similarity, but once it starts pitting inside, it can create a very significant pit inside the bulk material without being noticed outside. And the region or the area next to it on the surface can be intact with no corrosion at all. Okay? In the bottom row, the first image there shows crevice corrosion. Again, there is a metallic system joined to a non-metallic system in this case, and at the interface we can start corrosion, again by the difference of the potentials in the two materials. Stress corrosion, you can see there, it starts on the surface, it propagates into the material like a root of a tree. It can propagate through the grain boundaries of the material and can damage significantly. But in order for this type of corrosion to occur, there has to be one additional component, which is stress on the system. Okay? Now, selective leaching is the next type of corrosion. We all know that any material is not a single element. It has different elements, such as steel, for example. Besides carbon, it can have a lot of other ingredients, the steel. So it will form different phases in the material. Some of these phases might be more reactive with the environment and can be leached out. That is leaching corrosion. The last one right there is erosion. And as the image indicates, if you have a surface of the material where there is flow of it can be an aqueous system, liquid, or it can be gas. Anything that's flowing on top, it can cause erosion and corrosion on the surface. Let's take a look a little bit more in depth at pitting corrosion. Pitting is highly localized form of corrosion. It forms holes in the surface of the material, as we indicated before. It occurs in one specific area. in the area that becomes the anode, right, compared to the other regions. So the anode becomes corroded, and the material from there is being removed. And the mechanism is, remember, in the anodic area, we lose electrons. So we are losing electrons from the anode, and these electrons are going towards the cathode, which is the surface right there. It's in a reddish color and representation. So that part becomes the anode. And pitting starts, reacts and forms a pit, and the pit increases, and it can make a large pit inside the material itself. The reaction in the anodic area is iron solid, transforming into iron 2+ in the aqueous environment, plus losing the 2 electrons. In the cathode, the reaction is the oxygen in the form of gas, plus 2 molecules of water, plus gaining the 2 electrons, and that reacts into 4OH, that is the reaction. Pitting can cause failure with minimal weight loss, but significant damage. Okay? So that's why we look at pitting as we should be more careful with this type of corrosion. So I was looking at the Nature magazine and this last month, and I found a very interesting publication there where they did direct observation of pitting evolution. They used an 1045 steel, and they look at the surface, and they expose the surface of these materials to 2 types of environments. One is DI water, and the other one is sodium chloride solution. And as you can see there in the image, the rate of the pit density increases significantly when the material is exposed to sodium chloride, compared to when the material is exposed to the deionized water. It is, in the case of the deionized water, is much lower, the pit density. Okay. What they also did is they look at how this initiates. As you can see here, even at the microstructural level, they look at how the pit initiates. And what's interesting is that right there in the location where pit initiated, they measure high amounts of manganese and sulfur. This shows that manganese sulfide inclusions in 1045 steel can easily nucleate pitting corrosion. Okay? So, and that happens in 0.1 hours, right there as the image on the left shows. At longer times, 3.3 hours in the image on the right, it shows that the pit has increased in diameter, and also the manganese sulfide has been consumed in it. But pitting already started, and it will continue to grow. So it is important to talk about material selection, because in order to minimize corrosion or avoid those types of corrosion, choosing the materials with similar potentials will decrease the amount of corrosion. Okay? Choosing materials with dissimilar potentials, if the potential is significant or larger, then it will increase the corrosion of the more anodic material. The table right there on the right shows that more novel materials that act as cathodes are platinum, gold, graphite, titanium, silver, and the materials that would corrode much easily are zinc, galvanized steel, aluminum, mild steel, and so on. The key is that there has to be a well-thought design of materials that will go into the corrosive systems. Now, the economic impact of corrosion is significant. I think we can all agree there. Replacement, for example, if we need to replace a corroded equipment, we will incur in significant expenses, right? And if we over-design to allow for corrosion, we'll also have to take into account a lot of investment there. For preventative maintenance, for example, using painting, there's another expense. Or if we need to shut down the equipment due to failures, if the plant has large plant, that means a lot of money. Okay. if we contaminate the products, that means a lot of money. Loss of efficiency. And an example of that is, for example, in power plants, when the pipes where the steam is going through are new, the efficiency of heat transfer is pretty good. But as the pipe corrodes, it loses efficiency significantly. Okay, that means a lot of money, and so on. We can go and talk more about the impact of corrosion. But important items are, it can also affect safety, health, and depletion of resources. Okay. Let's look at the numbers. In 1978, the National Institute of Standards and Technology came up with a report. In that report, the total U.S. cost of corrosion was $82 billion. The same institution, NIST, in 2018 also has a report which indicates the total U.S. cost today is $330 billion. The avoidable costs in 1978 were $33 billion. Today, $133 billion. The unavoidable costs, $49 billion in 1978. Today, $198 billion. Those are significant numbers. But let's look at this other document. In 2013, NACE came out with the global cost of corrosion, and they indicated that it is about $2.5 trillion. I think the numbers speak by themselves here. These are the reasons why we need to worry about corrosion and why we're having this webinar. So let's go to the next topic today. We'll talk about, we'll introduce the NACE TG 516 test protocol.
Thank you, Juan Carlos, for the great introduction to corrosion fundamentals. But before we dive into the meat of the results from the CUI testing, what I'd like to do first is provide some introduction and background to the test we'll be describing today. We first presented results using the proposed NACE TG 516 protocol last year when we compared the CUI results with our insul-thin HT microporous blanket and a competitive aerogel blanket. Subsequently, after the webinar, because we received pretty good feedback from the engineering community and end users of our insulation materials, we decided to expand our testing using this protocol to 2 more of our products that we'll be reviewing this afternoon. To expand on the end user feedback, when I've spoken to several end users regarding this protocol, what they've told me is that they really value the results because the protocol is system-based and utilizes test conditions that, in their opinion, really mimic the real-world conditions they see in their processes. Furthermore, in the past year, a 3-year joint industry program, or JIP, was initiated that includes currently 17 participants. 7 of them are different end users in the industrial market, 4 coating manufacturers, and 6 insulation manufacturers, including Johns Manville. We've all signed up to fund the JIP based on this NACE TG 516 protocol, with the goal to better understand the effects of the different components and environmental effects on CUI. So like the JIP, the testing in this study was conducted by Southwest Research Institute, and they're located in San Antonio, Texas. SWRI is the same third-party testing agency that also conducted our first round of testing, as well as they've done a lot of testing using the same or similar protocols for other end users and manufacturers. The objective of this round of testing that we'll be talking about was to compare the CUI performance of 2 of our products. Again, that's the perlite Sprule WR1200 and our new water-resistant calcium silicate Thermo 1200. We also tested a competitive silica aerogel blanket as a baseline because this is the same blanket that we tested in our first round of testing. So shown on the left of the slide here is an exploded schematic of the test assembly that was used for this study. The pipe specimen was 2 inches in diameter by 12-inch length carbon steel that was then wrapped with different insulations that we just discussed, and then cladded with stainless steel covering to mimic actual pipe insulation and cladding installation. The pipe is installed in a box that is filled and emptied with water to get the system wet. In addition, a single hole is drilled into the bottom of the cladding and insulation to mimic what will inevitably occur in all systems, is the formation of a leak. During the test, the pipe is heated with an electric heater or cooled using blown air, depending on the condition that we want to test. And those are shown on the right side of the slide, which again shows two different conditions that were tested with this pipe specimens. The first is what we refer to as a cyclic or high temperature condition, where the system sees temperatures upward of 900 degrees Fahrenheit. In this condition, the pipe temperature is cycled between ambient and 900 degrees Fahrenheit throughout the week, but the system is also filled and drained with water to create cyclic, wet, and dry conditions. The second condition keeps the pipe temperature at around 45 degrees Fahrenheit, but again, the system is filled and drained with water throughout the week. We call this condition the sweating or low temperature condition. In essence, what this condition is representing is a system that remains below the dew point and remains in a continual wet state. For both of these different conditions, they were run for a total of 6-month time frame. So now that we've described the test assembly and the procedure, we needed ways to test the CUI performance of the systems. And we did this a number of different ways. Throughout the test duration, 3 different electrochemical methods were used to monitor the conditions of the 6 specimens to attain a corrosion rate. During the testing, the electrochemical methods provided somewhat of an indication of what was happening under the insulation without actually being able to see it or take the assemblies apart. In the first round of testing, the electrochemical results agreed very well with the post-analysis methods that were used after the systems were disassembled and measured using ultrasonic and optical microscopy. Again, the one difficulty with the electrochemical method is that even though they were useful in guarding trends during the 6 months, the quantitative measurements require the disassembly of the systems, which again include removing of the cladding and installations to actually get the pitting depth and rates. So now with that background, let's dive into the results portion of the presentation. As I mentioned earlier, in the last test sequence we presented last year, we tested 2 different hydrophobic blanket insulations, our Insulthin and a Silica aerogel blanket. This year, we looked at 2 of Johns Manville's preformed rigid insulations, the Sprule WR1200, which is an expanded perlite-based product, and Thermo 1200, which is a calcium silicate-based product. The perlite product is a hydrophobic insulation that has always repelled water up to about 450 degrees Fahrenheit. And our new calcium silicate product introduced last year and tested here is a water-resistant product that also sheds water, as can be seen in the middle picture. Finally, the third material is the same silica aerogel blanket that we tested last year, and we used that as a baseline comparison. Okay, so the first data set I'll be describing is what, again, I referred earlier as the low temperature or sweating conditions. This profile remained between 40 to 60 degrees Fahrenheit throughout the 6-month test, so the insulation and assembly remained wet the entire time. Each day, the sample setup would be filled with water in the morning by a technician and then drained at night. What's really important to point out, and it's noted in the bottom takeaway box, is that for the first 2 months of the test, tap water was used to fill the chamber, as can be seen in the right-hand picture. And in the last 4 months, a 1,500 ppm chloride solution was used to further accelerate the conditions of corrosion under insulation. So after the 6 months of repeated sweating cycles, SWRI disassembled the system. And what this entailed was removing the cladding and insulation from the pipes and then pressure washing and wire brushing the pipes to remove as much of the corrosion byproducts as possible so that we can get to the bare metal and examine it. And what we were able to discern from the specimens is that all 3 pipe specimens look very similar to each other after this low temperature test condition. So independent of the insulation materials installed on the pipes, all of them had uniform corrosion with very shallow pits. When Southwest Research Institute measured the pipes using the ultrasonic method, the average wall loss was about 5 to 8 thousandths of an inch for all 3 samples, so there really wasn't a statistical difference among any of the specimens. Next, we examined the impact of the high temperature cyclic conditions with the same 3 insulations. Here again, the same filling and draining of the water was completed, but now we included the 900 temperature condition. So each week, 2 cycles of high temperatures were exposed to the samples. So the assemblies were cycled between wet and dry conditions. And what this is mimicking is startup and shutdown conditions in field applications. Again, the same 2-month time frame with tap water and 4-month time frame with the 1500 ppm chloride solution was used. For the high temperature cycling conditions, the average, and I like to emphasize the word average, wall loss for the 3 installations were very similar. Because of the increased temperatures, the average wall loss increased to about 1/100th of an inch compared to the sweating conditions that we just talked about. But that being said, the more significant piece of data is that there was definitely a difference in the maximum pitting depth between the 3 installations. So keep in mind the deep pits, as Juan Carlos described earlier, are the ones that are less noticeable, but have the potential to be the most dangerous and lead to the unexpected failures in the system. With the data from ultrasonic techniques shown in the table here, the maximum pitting depths of approximately 25/100th of an inch were measured on the specimen insulated with perlite and calcium silicate. However, the pipe samples insulated with the aerogel blanket had a maximum pitting depth almost 3 times as deep at 71/100th of an inch. Based on the test results of the different measurement techniques, SWRI calculated the pitting rate in microns per year for the 3 different pipes, and those are also shown in the table. So again, this 3-time difference between installations is very significant, as the deep pits are usually the points of failure and also the most difficult to detect areas of corrosion, again, as Juan Carlos mentioned. One thing I want to keep in mind, though, is that these results that were shown here in this application that we tested had no coating. It was a bare carbon steel metal. It was also exposed to 1500 ppm chloride and the 900 degrees Fahrenheit. So, again, depending on the environment and application, these pitting rates will be different. One other significant observation that was seen with all 3 high-temperature cyclic samples was the formation of a magnetite layer on the pipes. The magnetite layer was very difficult to remove from the pipes, even with the wire brush that I described earlier. And what we observed was that between the 3 installations, the calcium silicate had the most adhered and thickest magnetite layer, followed by the perlite and then the aerogel blanket. It's important to remember, as I mentioned, that all 3 installations had similar average wall thickness losses. But what we're hypothesizing is that the magnetite layer that formed and remained on the calcium silicate and perlite actually can limit the formation of additional corrosion, and specifically the deep pits more than the aerogel blanket that we see here. Marybeth, in the next section of her webinar, will be elaborating on the magnetite formation. So the last set of data collected by Southwest Research Institute was the thermal performances of the installation over time. And so how they did this was the temperature of the exterior side of the cladding for each of the high temperature cycling conditions was measured with thermocouples throughout the 6-month time frame. And so what's shown in the table here is 2 things. First is the expected maximum temperature calculated using the online 3E Plus modeling software. The modeling is based on the pipe temperature, insulation thickness and type, metal cladding, and other representative environmental conditions. The second point shown in the table is for each installation is the actual measured temperature readings for the thermocouples. So what we can see here is that at the end of the 6-month test duration, the perlite and calcium silicate had cladding temperatures, or the actual maximum temperatures, lower than the expected max temperatures based on modeling. And what this means is the 2 installation systems insulated the pipes better than expected, or let less heat escape than expected. However, the opposite was true for the aerogel blanket, where the temperature difference between the expected and actual was 40 degrees Fahrenheit. And in this case, the actual max cladding temperature was higher than expected. This, of course, is very significant when engineering and designing installation amounts for process control, and especially safety. A higher actual temperature means you do not have sufficient insulation, and you actually need to use more insulation than expected. This is the second time that we've seen this large temperature difference, as we observed the same thing last year during our first test sequence with the same aerogel blanket insulation. That being said, we can explain this difference in expected versus actual thermal performance of the aerogel products because we know based on testing we've completed on competitive aerogel blankets as well as our own aerogel products that aerogels undergo thermal degradation of or thermal shift at high temperatures. We also know that the exposure of water to aerogels collapses the aerogel structure and reduces its thermal efficiency, and hence the lower performance than expected compared to the modeling as seen in this study. So that finishes up the results portion of the webinar, so now I'll hand it over to Marybeth to talk about our corrosion inhibitor work.
Thanks, Ames. In the next portion of the webinar, I'll highlight the basic premise of how JM's XOX corrosion inhibitor works and provide some additional data from laboratory testing to support the benefits of the corrosion inhibiting package. But before I get started, I just wanted to briefly touch on a couple of things that Juan Carlos covered in the beginning of the presentation. The first is material selection for mitigating corrosion risk. Material selection is critical to process design, but selecting the material that's most resistant to external corrosion may not always be possible. It may not be compatible with what is inside the pipes, or it may not be suitable for the temperature or pressure requirements of the process. Or it may just not be a justifiable cost at that time. So there are a lot of factors to consider when it comes to material selection. The second thing that Juan Carlos covered is that one of the necessary components for corrosion to occur is the presence of water or moisture in the system. Experience tells us that it's a great idea to keep water out of the system as much as possible. That's why there are so many hydrophobic or water-resistant insulations in the market, and why we cover insulation with robust jacketing systems. That being said, we know that water will almost always find a way into the system. It may be through poor installation, external damage, standing water, or even system leaks. In addition, hydrophobic treatments will usually burn off at a certain temperature, mostly above 450 degrees. So it's inevitable that the system will eventually get wet. The question then becomes, what happens when this occurs? So that's why the NACE TG 516 protocol that Ames just described is written and tested the way it is, and why end users approve of the testing. They know that wet systems are just a part of the process, and it's critical to dealing with understanding that situation. All right, so back to corrosion inhibitors. With our XOX corrosion inhibitor, there are two mechanisms at work to help inhibit corrosion with our Thermo 1200 or Sproule WR 1200. So the first mechanism that our corrosion inhibiting package uses to combat corrosion is through pH buffering. Low pH compounds from the environment can accelerate corrosion on the pipe surface, especially at high temperatures. When the XOX corrosion inhibiting compounds in the insulation come into contact with water, they result in a slightly alkaline environment. Those alkaline components in the system will neutralize any acidic compounds that may enter the system to keep the pH above 7. In the testing that Ames just described, we found that after 6 months of testing, the pH of the insulation next to the pipe surface was approximately 10 for both the Thermo 1200 calcium silicate and the Sproule WR 1200 perlite. The silica aerogel had a pH of about 7. So having the pH buffering component in the calcium silicate and perlite resulted in a higher pH at the pipe interface, likely resulting in lower corrosion rates. So the second mechanism that we will discuss is the formation of a silica-based surface coating. This occurs when water makes its way through the insulation and pulls with it the silicate anions in the insulation, leaving them on the pipe surface. And this creates a silica gel-based coating on the surface of the pipe. Over time, those silicate anions on the pipe surface can also react with iron compounds on the pipe surface to create an iron silicate coating. And you can see both of those mechanisms of formation in the equations on the bottom of the slide. Both of these coatings protect the pipe simply by creating an inert barrier to corrosive materials. And again, both of these mechanisms require water to be present in the system. We designed for it not to be there, but in the event that it's there, this is how the water-activated corrosion-inhibiting properties of the insulation will work to protect the piping. So one test protocol that we use and is pretty standard throughout the industry to evaluate corrosion on a laboratory scale is ASTM C1617. This protocol uses a liquid extraction on the insulation to remove any leachable compounds. That leachate is then exposed to heated carbon steel coupons repeatedly over the span of about 96 hours. And it's dripped onto the coupons in a way that the water is boiled off readily and that there's no pooling or standing water on the surface. But there can be some variance in this based on the person who's setting up the testing equipment. So after the 96-hour test, the coupons are then cleaned of any corrosion products and weighed. The weight loss of the coupons is then used to calculate a mass loss corrosion rate, or MLCR, in mils per year. In addition to the insulations, 3 reference samples are also tested at the same time, and they're deionized water and a 1 ppm and 5 ppm chloride solution. So it gives you a good reference for the relative corrosivity of the insulations against those standards. So as you can see in the table, the Thermo 1200 calcium silicate and Sprule WR 1200 perlite products have corrosion rates that are less than deionized water. The corrosion inhibitor both buffers potential corrosive ions and forms the silica gel layer to protect the metal surface, which results in the lower corrosion rates than DI water. The silica aerogel blanket, on the other hand, has an MLCR that's 3 times higher than DI water and almost 10 times higher than either Thermo 1200 or Sprule WR 1200. So although the data presented here is only a single test example, it's important to note that these results are very repeatable, as we've completed these tests numerous times over the last several years with these specific insulation types. So one of the questions that comes up a lot from end users is the longevity of the corrosion inhibiting package and if it ever runs out. So we decided to test this on the Thermo 1200. Based on the chemistry of the Thermo 1200, we know that the inherent composition of the calcium silicate material, along with the mechanism of silicate release, should not lead to a reduction in corrosion inhibiting properties over time. So in this test, we subjected the Thermo 1200 to repeated wet-dry cycles, and then used one of the test methods from ASTM C871 to measure the leachable silicate content of the Thermo 1200 over time. So what we found was that after 40 cycles, we did not see an appreciable drop in the silicate content. Therefore, we anticipate no impact to the inhibition performance over time. So earlier, Ames was covering the NACE TG 516 results. He talked about the formation of a thick and strongly adhered magnetite layer forming on the surface of the pipes that were insulated with the calcium silicate and perlite. So there are actually several different oxides of iron that can form as a result of corrosion. The one that most people are familiar with is hematite or rust. It's reddish-brown, flaky, and pretty easy to remove from the base surface. We did see some of that on the pipe surfaces at the end of the testing, as you can see in the image on the left. But the oxide that we found most prevalent on the calcil and perlite was magnetite. Unlike the hematite, the magnetite formation was very durable, uniform, and incredibly difficult to remove from the pipe surface. So we have listed 3 environmental conditions on the slide that drive that mechanism from hematite towards magnetite. So what drove the corrosion mechanism to form magnetite as opposed to hematite during the TG 516 testing, since all of the systems were exposed to the same conditions? And the big difference was the pH. Both forms of oxides or corrosion formed on all 3 pipes, but due to the higher pH of the Thermo 1200 and Sprule WR 1200 materials, the ratio of magnetite to hematite was higher. And again, keep in mind that the average total wall loss was the same for all 3 installations, but the ratio or amount of corrosion byproducts were different. Though both the magnetite and hematite are forms of corrosion, the more thermally stable magnetite is more preferred than hematite due to its potential to impede further corrosion. This is evident in the fact that the aerogel sample had deeper pits than the other 2 installations, potentially due to the lower degree of protection from the hematite layer compared to the magnetite layer. So when we talk about corrosion under insulation, we always speak in terms of inhibiting or mitigating the effects of corrosion. And that's because based on the requirements of corrosion, it's not really a question of if, but when and where all of those components will be present. As Juan Carlos covered in the beginning of the presentation, there are a lot of different types of corrosion and a lot of different mechanisms of corrosion. And as our testing found, not all corrosion products are created equal. So there's really no one-size-fits-all solution to corrosion. Material selection, whether it's metallurgy or insulation, is critical to designing systems with a robust defense against corrosion under insulation. And corrosion inhibitors can play an integral role in slowing corrosion and protecting the pipe surface. That's why looking at the system in the process is more relevant and being able to vary the environment in which the system is tested is critical. As insulation manufacturers, we can design our products to be more water repellent, coating manufacturers can design coatings to be more robust, and end users can design their processes to most adequately comply with their environmental or process conditions. But there will never be a perfect world where something isn't going to go to plan, and that is why it's imperative to test and design for all possible conditions so that the most informed engineering decisions for each application can be made.
All right, well, thank you, everybody. With that, I'm just going to go through some additional resources that we have before we get into some questions. First and foremost is that we do have an ebook that actually covers all of this content we went through in great detail today. We're actually going to be sending you this ebook via the WebEx Event Center right now, and then if you don't want to download it now, you can download it later when we send out the recording of the webinar. So look in your chat box. That's where that should be coming through. The second resource I'd like to discuss is called The Source. Now, this is a portal on our website where you can access our free recorded webinars, blogs, product documents, specifications, training tools, etc. This is where you're going to find our first webinar that Ames referred to on the NACE TG 516 testing, where we compare two thin blanket insulations, as well as additional webinars on corrosion, industrial acoustics, material specifications, and more. Now, regarding our blog, we write and curate content for our blog so that we're not only relying on our own technical experts at JM, but we also have information from technical experts throughout the industry so that our blog topics hit on targeted information that is rich and robust and relevant to you. There's also a full library of helpful documentation on The Source. This is where you can find things like technical bulletins, white papers, product application guides, etc. We strongly encourage you to browse this section if you're looking for detailed information about our products or leading industry issues. And finally, in the tools section, you'll find things here like the NAMAS 3E Plus program that Ames referred to. You can download our Smart Binder app. This is where you can get access to our data sheets, safety data sheets, that sort of thing, right there on your cell phone. And then we also have the product application rating tool. Now, this is where you can actually use your application requirements to do a side-by-side comparison of our products using this tool. So for everybody who attended the live webinar today, you will receive a certificate of completion following this webinar. That's going to be sent to your email directly on Friday. So with that, let's go ahead and get into some questions. Now, the first question we have is, it's for you, Marybeth, and that is, you mentioned the XOX corrosion inhibitor. Is that, which products is that available with?
So the XOX corrosion inhibitor is a part of our Thermo 1200 calcium silicate and our SPRULE WR 1200 perlite products.
Excellent. The next question we have is for you, Juan Carlos, and it actually refers all the way back to one of your early slides on reasons for corrosion to occur. They asked about the first photograph on the left. Does that indicate dissimilar metals, or is it applicable for similar metals? And so Juan Carlos is actually looking at the slides right now, and he'll run through that for us.
So the answer is this is when you can have two different materials joined together. Okay, that creates different potentials.
All right, perfect. The next question is for you, Ames, and that is, does the fill-drain procedure take into account impingement of loosely adherent corrosion products?
For the answer to that, I just want to clarify how that test procedure is completed. The system, so the pipe with the insulation and cladding, is not removed at all throughout the 6 months, but the water that is filled and drained is filled with, obviously, with a hose and then drained with a vacuum, and then there's new water that is used each time that fill-drain procedure is conducted.
Excellent. Marybeth, maybe you could dive into this. There was actually a question if we could show the corrosion inhibitor. So I think there's maybe a little bit of a misunderstanding about what that is. So could you describe what that is and how that plays into our products a little bit better?
Could you repeat the question? Sorry.
Yeah, the question was, can you show the corrosion inhibitor? And obviously that's not something we can really show. So
no,
could you dive into what it is?
It's a part of the insulation, and it is, again, like I said, water activated. So it's not something that we can actually show. It's more of just the mechanisms of inhibition that happen as a result of the properties of what is in the insulation itself.
Excellent, thank you. The next one is for you, Ames, and that is, the up and down temperature results are interesting. My question is, what were the results of a sustained elevated temperature exposure?
So in this particular, I guess I'm struggling with the question. Throughout the 6-month time frame, we had cycles of high temperature and low temperature. We did not remain or keep the insulation at 900 degrees for the entire time. And the main reason for that is the study with the NACE TG 516 is to look at corrosion. And as we've mentioned, corrosion doesn't occur without the presence of water. So that's the reason why we didn't do it at just 900 degrees Fahrenheit.
Excellent, thank you. This one's a little vague, so I'm going to pitch it out to the group. What are the unmet needs of CUI coatings? We're obviously not a coatings manufacturer, so that may be one we'll actually take offline. So the next one we will get to is, could you repeat the temperatures used in the low temperature cycling?
So the temperature was about 45 degrees Fahrenheit, and it kind of ranged between 40 to 50 degrees.
Excellent. And has any of this testing been conducted on foam glass insulation or closed cell elastomeric insulation material?
So this protocol has been used on other insulation manufacturers, or other insulations and manufacturers, but because we did not do that testing, I don't feel comfortable with presenting those results.
Excellent. Marybeth or Ames, this one's for you, and that is, has the magnetite layer been measured, and if so, how thick was it?
Yes, we can get back to that question. It was measured using optical microscopy.
Okay, we'll look that up and come back to it. Juan Carlos, this one might be more accurate for you. Will a spacer between the insulation and the pipe help mitigate CUI?
Well, it depends what the material of the spacer is. If it's well designed, it probably can mitigate. But remember, if you have the components for corrosion to occur, we're talking about aqueous corrosion. Again, I need to stress on that. Then if all those components are present, then the corrosion will happen. The problem is, what is that intermediate material that you want to put in there? If it's more corrosion resistant, probably you can help a little bit with the system, but it really depends what you put in there.
Okay. Ames and Marybeth, I'm going to have you guys speak to this. They did ask if a thermal spray coating has ever been used in the testing, and I think you might want to give a little bit of background on the testing there.
So in our first round of testing with the insulfin, we did use thermal spray coating. We had a thermal spray coating on that system, and so I think Kim said that you would provide the data, or not the data, but the eBook that also includes that scenario into the testing. And what we showed is that the insulfin did not have any impact on the thermal spray coating.
Okay. The next question we have is did you actually test your insulfin product versus calcium silicate and perlite? And if so, what were the results?
So we did in this test, again, it's a 6-month time frame, so we have to be selective of which products or scenarios, applications that we test. That was the reason why we looked at the aerogel blanket. So again, in the e-book, if you take a look at both test results, you can kind of make a comparison of what they would look like.
Okay. There seems to be a couple questions around XOX and whether it's something you order, whether it's integral to the product. Can you one more time reiterate which products it's on and whether or not you order it? Or
So yeah, the corrosion inhibitor is it's not a coating or anything like that. It is an integral part of the insulation itself in both the Thermo 1200 and the Sprule WR 1200. You can't just buy the corrosion inhibitor. It is specifically a part of the insulation. And as far as being used with a paint or a coating, we've only tested it with the bare metal, so I can't really comment on any performance with a coating application. We don't anticipate that there would be any sort of negative impact with a coating.
All right, excellent.
That being said, to add to that, we've been selling the corrosion inhibitor since 2002, and so we shouldn't see any problems. That being said, different manufacturers have different formulations, and the XOX is proprietary to our system. We have ASTM C1617 data that does show marketed difference between the different manufacturers of calcium silicate. And there was also another question that we found the answer to, and it was actually in the slides. The thickness of the magnetite layer that we measured was from 0.006 of an inch, was where the aerogel blanket was, to about 2300ths. So there was a 4-time difference between the aerogel blanket versus the perlite and calcium silicate in the amount of magnetite that formed.
All right, the next question is, has any testing been done on systems with cathodic protection?
We have not with this particular protocol.
During this testing, is the pipe cycled between 900 degrees and ambient while it is submerged in water, or after it was allowed to drain?
So it's actually allowed to drain before it has reached 900 degrees Fahrenheit.
All right. The next question is, and I'm not sure on this one, has this insulation method being used for downhole casings? We're not quite sure what that question means. If you want to add a couple more details around that and resubmit, we'd be happy to come back to it. Okay.
You know, it would be, I'm just thinking downhole casings, it would be more difficult to use in those conditions. If somebody's using in those conditions, we would like to know that, right? But I've not heard that somebody is using those conditions.
Okay. Have you tested if the magnetite layer has any effect on ultrasonic thickness reading?
We haven't tested. When we were looking at the magnetite, it was using the optical, and so we also, again, there were a bunch of different test methods, electrochemical as well as optical and ultrasonic, so they all, when SWRI looked at the results, they aligned pretty well.
Okay. Was the test solution replaced during testing, or was the same electrolyte used throughout?
It was replaced every single time.
Marybeth, is the inhibitor compatible over any coating material system?
Yeah, I guess the only thing that I would keep in mind is that it is going to create a slightly, again, alkaline environment. Make sure your coating is going to be compatible with that higher pH.
Okay. This one kind of deviates, and so we might choose to pass it off, but how can I avoid the damage in stainless steel piping with a fiberglass cover? And Juan Carlos, you might be able to speak to that a little bit better. So if they have fiberglass insulation, what could they do to help avoid corrosion?
The question is very broad, very broad. You know, the types of answers would be unique to what you're trying to do, what a specific application is. I think one solution is using the products that Marybeth was explaining before. Again, it's very open question, this one.
Okay. All right, we can get back to that. And then the final question we have is from the galvanic corrosion, Juan Carlos. Does the contact surface with the noble material require some sort of exposure before this is activated?
No, remember, the key here is if you have the component for aqueous corrosion to occur, it doesn't matter if you prepare or not prepare before the system is put together. Corrosion will still happen, right? So it really depends how you put together the parts, the component with this noble material or not. And if there is some electrolyte outside, corrosion will happen.
Okay, great. We do have one more question, and that is, do you have any data on how the protocol correlates with real-world conditions or operator experience?
Yeah, so one of the reasons why we're very in tune with this is we have had end users who have compared the results of the TG516 protocol with field conditions that are similar to the test protocol conditions, and they've communicated that there's some very good correlation between this protocol and what they've seen in the field.
Okay, excellent. We did have a couple last-minute questions come through, but we're going to go ahead and wrap it up. For those questions we did not get to today, we will actually reach out to you privately and make sure you get your questions answered. So that does conclude our webinar. As I mentioned at the beginning, we will be sending out a survey immediately following, and we would really appreciate it if you take a little time to offer us your feedback. And again, if you have any questions that you were unable to ask today, or maybe you think of it afterward, you're certainly welcome to submit those via the survey, and we will reach out to you directly. So the webinar recording will be posted later this week or in the next couple of days, and we will send you an email with direct access to that as soon as it's live, as well as a link to our eBook regarding all of this information. So please keep an eye on your inbox for your certificate of completion. Again, that's going to be to you by Friday. Thank you very much for attending, and we hope you found the information useful and relevant. And if you have any questions, please don't hesitate to reach out to us directly or via the survey. Thanks so much, and enjoy the rest of your week.